Hi, I'm Dominik, and today I'm going to talk about how we can design soft robot hands from demonstrations. Unfortunately, humanoid robot hardware isn't really available to buy off the shelf, so you can't go out and buy a humanoid arm or a hand or a leg. So what do we end up doing? Well, we build our own custom robot hardware. But the problem with that is there also isn't really an established design process yet for building humanoid robots. So this is especially true for dexterous and soft robot hands. So in our experience, we often end up building a lot of prototypes to figure out what works and what doesn't. And this picture here on the left shows just a few hands our lab has built over the years. And of course, every prototype and every iteration can be very time consuming and costly. So what if we could change this? What if instead we start with a set of important tasks and then we automatically generate a hand design from a set of demonstrations? How can we do that? We start with motion capture trajectories of the task demonstrations and an all-spherical joint hand model that has 18 joints and 54 degrees of freedom. We then adjust the link lengths and joint locations with the model through optimization such that they can match the trajectories. So now we have a hand model that can reproduce the task demonstrations, but it still has 54 degrees of freedom, so that's not very practical. Well, we can reduce that number without sacrificing capabilities by finding the dominant axes of motion for each joint. This allows us to reduce the degrees of freedom in each joint from 3 to 1, so we end up with 18 degrees of freedom, which is a little more practical. Based on the resulting hand model, we can then use a library of link templates to automatically generate a fully printable CAD model. We then print the hand design in a single print, and after a few hours and removing some support, we do have a functioning soft robot hand. So to conclude, I have shown an end-to-end process that allows us to create soft hand designs from human demonstrations. Now, of course, due to time, I had to leave out a lot of details, but I want to point out here that we have extensive experience with evaluating and controlling these types of soft robot hands. These hands can be easily controlled using teleoperation or open loop control, and they're surprisingly strong, very durable, and they last thousands of actuations without breaking. Thanks for listening, and please come see me at the poster session if you want to learn more details. Thanks.
Hi, I'm Joey Byrnes, and I developed the low-level control and electronics of Tello, a dynamic biped created at UIUC's Robodesign Lab. Tello is designed for research in dynamic telelocomotion. A human pilot takes steps in our human-machine interface, or HMI for short, and the dynamic data of the human is transmitted to the robot controller. Tello's controller tracks a scaled version of the human's divergent component of motion and sends force feedback to the human such that the robot and human remain dynamically synchronized. This allows us to leverage the human pilot's decisions and subconscious reactions to plan motions and stabilize Tello. Tello's controller is a single-board computer running a Linux kernel built with the preempt RT patch. This gives us the flexibility of Linux while having the benefits of a real-time OS for deterministic program execution. Tello's control algorithm updates at 1 kHz and is spread across 7 isolated CPUs. And Tello makes use of high-performance motor drivers and sensors with high update rates to keep up with its agile dynamic motions. I've designed a variety of custom electronics for Tello, including load cell amplifiers for reading the ground reaction forces, encoders for measuring the joint position and velocity, and a power management PCB for voltage regulation, battery switching, safety features, and more. Tello's control software is written in C++ and spread across 7 isolated CPUs. CPU 0 is used for running the essential kernel tasks that are required for Linux to work, while CPU 1 runs Tello's main control thread. This includes the PD control for the legs, the balancing algorithm, the telelocomotion framework, and finally sends commands to Tello's actuators. All data received by Tello's controller is done asynchronously in separate threads. CPU 2, for example, is used for receiving CAN messages from the motor controllers, joint encoders, and load cell amplifiers. And CPU 3 is used for receiving UDP messages and UART data from the IMU. One source of UDP data comes from our custom user interface for running our experiments, and another source comes from the human data captured by the HMI. CPU 4 is used for our state estimation. When data is available from our lab's motion capture system, This thread receives mocap data, giving Telo's center of mass position in the world frame. And when no mocap data is available, we use Ross-Hartley's contact-dated invariant EKF to estimate Telo's world pose from its kinematics and inertial measurements. CPU 5 is reserved for data logging. About 175 values are logged every millisecond, and the log data can be played back later on CPU 6 as if it's coming from the HMI in real time, and this allows us to tune gains and test new features without needing a pilot in the loop. Finally, CPU 7 is used for a prediction algorithm that monitors the human pilot's foot motion and predicts how long their step will be and how high it will be so that the robot can track a similar trajectory in real time. Here we have a block diagram for the software running on Telo's main control thread on CPU 1. The high-level controller computes the required ground reaction forces for balancing, and the reference trajectories for Telo's feet during their stance and swing phases, while the low-level controller handles tracking those trajectories and converting all of the forces and torques down to the motor space, as well as passing all of the state feedback back to the high-level controller.
Hello, my name is Grzegorz Ficht. I'm with the AIS group at the University of Bonn, and this is Improving Humanoid Dynamics with Hardware and Software. First, let's take a look at the open source Nimbro P2 robots that I've designed and built. Although they are reasonably tall and lightweight for their size, they follow the usual design scheme with actuators placed at the joints. It's a research platform that our team Nimbro uses for RoboCup, where we have won the tournament 5 times back-to-back, as well as other awards. As you can see, the performance is quite robust, allowing it to autonomously score goals even in tough conditions. However, with the underpowered actuator and actuator joint collocation, it is approaching the limits, and more dynamic movements are beyond its capabilities. If we look at modern control approaches, a common point is to reduce the reflected inertia, which increases the control bandwidth and durability, but also allows for simplifying the dynamics to where real-time control of highly dynamic motions becomes tractable. So one way to improve dynamics is to design limbs with low reflected inertia, like this 3D printed leg prototype that I designed in 2020, which only weighed 2 kilograms, and only 2 QDD actuators were sufficient for a planar leg. The foot position was constrained with a parallelogram and made compliant by using carbon fiber plates acting in springs. Here you can see the leg performing jumping simply by using impedance control and active compliance. By adding an extra 8 kilograms of weight, the single leg was still capable of jumping, which demonstrated that a running humanoid could have been produced from this design. If limb dynamics are too significant to be ignored, it's best to include them in the design of the controls. Using a simple triangle approximation, I found a one-to-one mapping between the limb kinematics and its mass positioning. I then combined the masses of each limb and the torso into a 5-mass representation of a humanoid, where the relative movement of each mass shapes the overall inertia. This then not only defines the system's COM, but also its angular counterpart in the form of the orientation of principal axis of inertia. Desired dynamical effects are then achieved by manipulating the COM position, inertia size, and orientation. From these values, my whole body inverse kinematics approach then produces the necessary joint trajectories. I've combined this approach with a set of regulators into a framework, which allows for simultaneous linear and angular momentum regulation for disturbance reduction. Other benefits of modeling the limb dynamics include a refined centroidal state estimator, where the ZMP and CMP can be obtained without having access to foot sensors, as well as a feed-forward controller where the feed-forward terms are applied on the centroidal level, which abstracts the joint structure. The complete framework has displayed impressive disturbance rejection capabilities during this year's RoboCup, where a robot took the first place in the push recovery challenge. Thank you for your attention. These are my references.
Hello everyone, my name is Yunho Han, and I am a researcher taking the PhD course at Korea University in Republic of Korea. I'm interested in the field of bipedal robots and humanoid robots. So I'm currently studying locomotion planning and control for bipedal walking. Recently, I have been focusing on developing an optimization-based walking control framework. Furthermore, I'm considering the concept of an optimized leg design for efficient leg movement. Since 2022, I have redesigned the humanoid robot Loco 3 to change from joint position control to joint current control based system. And I have conducted various tests to confirm the torque control based operation and performance. One of the experiments I have conducted was maintain its balance on the change slope. Then I introduced the full body dynamics model based whole body control additionally. And I also made attempts to integrate MPC and whole body control. However, the biggest challenge was that there exists a significant difference between simulation and reality while conducting research on torque control-based working. For me, the significant difference factor between simulation and reality was that friction of the joint. Block 3 uses high reduction gear harmonic drive, which with a reduction ratio of over 100 to 1. Consequently, the high reduction ratio of the gears causes the high friction in each joint, leading to a difference between the torque command and the actual joint torque output. This problem can degrade the torque accuracy and response speed of the joints. Most robots try to solve this problem by attaching torque sensors at each joint. However, Block 3 does not have torque sensors for sensing the torque of joints. Therefore, I attempt to address this problem through joint friction compensation. I applied the friction compensation based on Coulomb and viscous model. And currently, I'm looking for other methods to compensate for friction. If anyone has an interest in or ideas about this issue, I would appreciate them. Thank you for listening.
Hello, I'm Ernesto, and I'm a recent PhD graduate from the University of Illinois at Chicago, and I will be presenting a small portion of my research in model adaptive control for real-time parameter tuning. One approach to controlling bipedal robots like Digit shown here involves modeling the physical behavior of the center of mass of the robot by fitting an analytical model to the center of mass kinematics. In the simplest case, the first-order regression function can be used to map the states of the robot at a specific instance of the gait cycle to the predicted state after an arbitrary time has elapsed. The linear inverted pendulum is one such model that is commonly used for this control. However, the physics of the robot may change in real-world scenarios when the robot is carrying a load or when the robot is walking in uneven terrains. The plots here, they depict the velocity on the top and position at the bottom of the robot center of mass during walking using a model-based controller. The predicted position and velocity exhibit modeling errors that lead to a tracking error in the velocity tracking. It is therefore important for such analytical models to have adaptive parameters that can be tuned in real time to enhance control. One approach to fix the tracking error is to add a feedback term to the tracking controller such that the tracking error converges to 0. However, the controller tackles the tracking problem without actually improving the modeling error. One type of model adaptation that can be utilized is the model integral feedback controller, in which an error feedback term is added to the model such that the model errors in position and velocity, they slowly converge to 0, and the speed of convergence is determined by the gain matrix Ki. And then the plot here shows the velocity and the position data during a forward walking simulation where the model used to the control is incorrect. And so when the time reaches this dotted line, the model adaptation is turned on, and the modeling error as well as the tracking errors converge to 0. Another approach is using the recursive least squares algorithm to find the augmented parameter coefficient R by using the error covariance matrix and common gains as model feedback terms. Here, the plots again show that when the adaptation is turned on, the modeling errors and the tracking error approach 0, and the bottom plot shows the value of the augmented parameter coefficients. Here's a simulation where the height, step width, and toe damping of the robot is changed during forward walking. The top video shows a trial where no adaptation, and you can see the robot eventually will lose its stability and fall. And then the bottom video shows a trial where the adaptation controller is turned on, achieving greater stability and greater tracking. And then we see the coefficients, how the coefficients adapt here in the. Here's a hardware implementation trial where the robot's height and step width are varied to add variability in the robot's physics. The desired velocity here is the dotted line, and dictates manual user. Initially, there's a large velocity tracking error, which eventually decreases as the adaptation occurs. Thank you for your time.
Hi everyone, I'm Donghyeon Kim from Seoul National University, and I'm delighted to present torque-based reinforcement learning on biped robots in this CWBB workshop. Recently, reinforcement learning on robots has garnered significant attention, aiming to overcome the limitations of model-based approaches. As illustrated in the figure below, most studies in this domain have focused on learning target poses and employed lower-level PD controllers in specific games. However, a drawback of this position-based method is its dependence on PD gains, which vary with tasks and robot hardware. Therefore, tuning gain becomes necessary for each task and robot configuration. Moreover, the position-based approach lacks compliance, posing challenges due to the existence of reality gap. The reality gap results in mismatched contact timing, and when unexpected contacts occur, the PD controller generates large torque, resulting in limited compliance. Our approach, on the other hand, involves directly learning command torques, offering several advantages. One notable benefit is the elimination of the need for gain tuning depending on specific robots and tasks. Additionally, the torque-based method exhibits enhanced compliance, rendering it more robust in bridging the reality gap. This video demonstrates the compliance of our torque-based method, showcasing its effectiveness in handling uncertainties. Lastly, contrary to conventional knowledge in model-based torque control method, which adopts high control rate, our findings indicate that the control rate can be reduced to 62 Hz. As a future work, we are aiming for RL-based real-time motion retargeting on physical robots, particularly focusing on locomotion. Thank you for your attention. If you have any questions, please don't hesitate to reach out. Thank you.
Welcome to my presentation, Can we build Baymax, on the actuation and kinematics for humanoid robots with human-like motion. I'm Cornelius Klas, research scientist and mechanical engineer for humanoid robot design at the High Performance Humanoid Technologies Lab at the Karlsruhe Institute of Technology. At our institute, we have built several humanoid robots, actuation units, and hands in recent years. One of our latest robots is ARMA-DE, a humanoid robot with an omnidirectional mobile base, two 8-degree of freedom arms with exoskeletal structure, and sensor controller units in all arm joints. It also includes height adjustment and humanoid hands. I dream of soon having humanoid robots with human capabilities. My research revolves around the question, why is it so challenging to achieve human performance, while electric motors can have a higher power density than human muscles? The three identified challenges are: exact requirements for human motions in terms of torque, speed, and acceleration are not known. With actuators placed in the joint axis, there are large inertias across the kinematic chain, and the actuator force torque profile and internal inertia do not fit the requirements. The following three topics address these challenges: a robot design tool to derive the requirements from human motion, a novel joint mechanism and new kinematics, and a linear drive for torque velocity profiles similar to those of human muscles. A key in the system for humanoid robot design is the derivation of normalized actuation requirements from human motion. The input are different humanoid robot kinematics and sets of human motions. Both human motion and robot kinematics are first normalized. Then the motion is transferred to the humanoid robot. With this motion, the joint torques are calculated. The result are the normalized actuator requirements. Here, the requirements are analyzed for 4 different sets of motions. As a result, the normalized velocity, acceleration, and torque of all arm joints of the different robot kinematics and the complete arm actuator power requirements can be compared. Thank you for your attention.
Hello, my name is Niranjan and I'm a PhD student at Georgia Tech. My research focuses on designing learning frameworks to build data-driven controllers for legged robots. More specifically, I'm interested in building frameworks that lets us create diverse, robust, and expressive policies for humanoid robots. To accomplish this goal, we need an architecture that scales without extensive human engineering to new tasks. In this spirit, my recent line of work uses human motion trajectories to train robot control policies. My approach allows the user to just tell the robot what he wants it to do. A neural network control policy is then trained with the user input to control the robot and then perform the task. I accomplish this by combining a large language model, a text-to-motion model, and a motion imitation approach to convert user language commands into robot control policies. My approach also enables the user to interactively correct the robot's motion so that it aligns more closely with the user's intention. Using this approach, a diverse set of skills can be generated without requiring any complex reward engineering or model-based controller design. But in cases where we do not have a dataset of human motion to guide the robot, we have to either manually engineer controllers using traditional model-based approach or use reinforcement learning to train the robot and maximize the reward. This doesn't scale well because as the task complexity increases, the extent of reward engineering that's required to get the policy to work becomes impractical. In my earlier work, I proposed a solution to this problem by building new policies to solve new tasks as combinations of a library of skills which can either be learned or designed using model-based approaches. For example, we can train a robot to turn by perturbing a walking policy. We can then teach the robot to reach a target by perturbing a mixture of walking and turning policies. Using this approach, we build a hierarchy of policies with every level in the hierarchy dependent on skills learned in the previous level. CCRL enables us to train a robot to perform complex interactive navigation and object manipulation tasks that transfer reliably to the real world due to the hierarchical and modular nature of our framework. One common drawback with learning-based robot control methods is the sim-to-real gap, where the policies trained in simulation do not transfer well to the real world. In my prior research, I looked at this problem from a parameter discovery perspective, where I used Bayesian optimization to tune the simulation parameters so that the robot performs well in the testing environment. In addition to legged robots, I also have experience in robot manipulation, particularly in interactive perception with manipulator robots. In the work shown in the video, I built a framework that lets a robot interact with a cluttered scene and discover hidden objects. In another related work, I developed a framework that lets a robot discover the physical properties of an object by interacting with it. I'm in the job market for full-time positions. Please reach out to me if you have any potential opportunities.
Hello, I'm Daegyu Lim, a PhD candidate at Seoul National University. I will present my research titled Proprioceptive External Joint Torque Estimation for Humanoids via Uncertainty Torque Learning. The surge in developing general-purpose humanoid robots demands them to safely share workspace with humans. But a major challenge is ensuring these robots can detect and respond to unexpected collisions to prevent falls and ensure human safety. To resolve this challenge, I propose MOVNet, a novel sensorless external joint torque estimation method. It combines a model-based disturbance observer with deep learning to accurately estimate external joint torques, overcoming model uncertainties. Here is a demonstration of external joint torque estimation when the robot works randomly on uneven terrain. The blue dotted line shows the measured external joint torque using full torque sensors. The red line represents the estimation of the proposed method, MOVNet, compared to the green line for the end-to-end learning method and two gray lines for model-based algorithms. MOVNet and FTS-E2 method outperform model-based algorithms for in-distribution data. Additionally, in the collision test, an out-of-distribution scenario, MOVNet shows the lowest estimation error, demonstrating its robustness to unseen data, while FTS-E2 shows much increased errors compared to the in-distribution data test. The MOVNet's accurate and robust estimations allow for various applications. First, contact wrench feedback control for stable working without force torque sensors. Second, collision detection and reaction approach of humanoid robots. Third, an intuitive hand guiding method for moving the robot. In summary, MOVNet contributes to the accurate external joint torque estimation of humanoids only with proprioceptive sensors. Finally, MOVNet can decrease the cost of humanoids and enhance the safety of humanoid robots. For more details on my work and other projects, please visit my personal page. Thank you.
Hi, my name is Yunho Han, and today I'm very excited to share our development of interactive and practical design tool for creating actuation system of humanoids. Design of actuation system for humanoids is tough for many reasons. When we design a humanoid from scratch, we start with basic parameters such as height and weight. Based on these parameters, we come up with motions such as walking or carrying boxes. Now, a designer needs to find motors and linkages to bring those motions into the real world. A major issue here is that design optimizers typically run slow because the design space is so huge and not smooth at all. Practicality is another important matter. For example, designers need to check if a candidate design is physically feasible or not. In this process, designers rely a lot on expert knowledge to reduce engineering work. So what we propose is a better design tool that is interactive so that we can embed expert knowledge and gain new intuition. And also fast so that we can do more iterations and try different ideas. Here's a quick overview of design tool that we are proposing. First, a designer needs to provide information and knowledge as much as possible about the target design. That is to say, a designer needs to curate a robot model, design motions, design libraries with components they find useful, followed by goals and custom design rules that are relevant to design target. Next, a numerical programming will figure out the best design for you. Then this process iterated a few times. To make this process faster, we have employed special technique. For those who are curious, please come to the poster session. We ran design studies using this method. You'll see robot doing weightlifting and fast walking. What separates this tool from other software is that it is made easy to reason about a single robot doing multiple tasks. It guarantees some safety design by respecting hard system limitations, while other methods usually rely on soft constraints. And finally, it is useful in a wide range of stages of design. To summarize, I'm proposing a design tool that's not only fast, but also interactive for more practical results. Briefly saying, this design tool converts rough design envelopes into detailed designs. And I believe this will bridge the gap between controls and hardware engineers, especially in the industry settings. For those who are questioning if this idea is actually useful, please wait a little bit. We're developing a new humanoid named Dash using this method. And thanks for listening.